Okay, I think that's us. So this afternoon we are absolutely delighted to welcome Neil Sheldon, who is going to be delivering a kind of modified version, I think, of the Teaching Statistics Trust lecture. So Neil, if I remember rightly, so Neil has been a teacher for more than 40 years as a chartered statistician and the former vice president of the Royal Statistical Society. He's also been the RSS Guy Lecturer in 2007 to 2008 and is currently the chair of the Teaching Statistics Trust. And it's in that capacity that Neil is talking to us today. So the talk that he's going to deliver is, we need to talk about statistics. The purpose of statistics is insight, not numbers. And I suppose I should just pass over so that we've got the main event happening. Neil.
Okay, thanks very much, Kate. And welcome to my Teaching Statistics Trust Lecture 2019. And it is 2019. The lecturer is appointed for a calendar year. This is a version of the lecture that I gave last year. And the last count, it was 123 people listening in. So I think that means that this is the biggest audience that the lecturers had. I gave it about a dozen times last year. You'll see from the front screen there that one of the things that I'm involved in is linguistics. And I have for many, many years had a deep interest in linguistics and actually the philosophy of language. And that is a big influence on the sorts of things that I want to say today. Well, to get started then, let me just say a little bit about the Teaching Statistics Trust. It might not be familiar to everybody, but the Trust publishes the journal Teaching Statistics. It does promote statistics in schools and colleges, it funds initiatives, but relevant to today, it delivers the Teaching Statistics Trust lecture. The first lecture was in 2017, David Spiegelhalter, 2018, Christine Franklin, who's an American Statistical Association ambassador, 2019, me, 2020, for obvious reasons we haven't been able to organise a lecture, and 2021 it'll be Chris Wilde from Auckland, always assuming that everything is back to normal. Now, the TST lecture is aimed at teachers, reasonably enough. I have modified it to some extent because I suspect in this audience there are going to be quite a lot of people who are not teachers. But when it's aimed at teachers, it's not a matter of do I understand this, it's a matter more of do my students understand this? Am I using the best possible language to convey this to my students? I say that because some of the points that I want to make, I think you'll probably find elementary and straightforward. I don't think all of them are by any means, but some of them will be. And if that is the case, then think about your own communication. As I say on this slide here, for the broader audience, it's got to be a case of saying, do the people I'm speaking to, my audience, actually understand what I'm saying? Am I using the best possible language to convey my message? These are the sorts of things that I think we as statisticians ought to be saying to ourselves. Now, statistics, of course, can mean two things. It's the subject, but it's also the numbers that the subject studies. And my title is deliberately ambiguous. When I say we need to talk about statistics, I'm saying we need to talk about the subject, particularly in the light of curricular changes and some other changes that I'll mention. But we also need to talk about the figures that the subject studies. My point here is it's not enough just to collect the data and do the arithmetic. The really important element is actually discussion, interpretation, explaining what the figures tell us. Just to expand on that a little bit, and forgive me, this is English-centric a bit, but statistics in schools is changing. In England, we have core maths, we have a new A-level in mathematics, and both of those recognize the importance of interpretation in statistics in a way that simply wasn't present in the qualifications that went before that. You may or may not have come across the International Data Science in Schools project. If you haven't come across it, I would suggest that you look it up. There's the web address there. And it's a very interesting initiative. designed to introduce data science into the school curriculum. And with that sort of thing in mind, with technology, with big data in mind, well, it's increasingly the case that calculations, drawing of graphs and so on, that used to be the staple of statistics teaching, is recognized now as being best done by human beings, not by people. And of course, once you're into big data, you've got to use computers. And that leaves room, a very important space actually, for people to interpret data. It's only people that can interpret data, and interpretation requires careful, precise, nuanced use of language. So what is statistics all about? Well, it's all about understanding the real world. It's about problem solving, inference, interpretation. It's about the communication of conclusions. And all of these activities do require students to use language with care and precision. They need to understand the meanings of terms. They need to know how to express themselves clearly. And this focus on the use of language is growing as specifications and assessments change. But, and this is a point I make quite a lot of when addressing groups of teachers, it can be unsettling to teachers that were brought up in a different tradition, particularly those who think of themselves as pure mathematicians and are perhaps not comfortable with the language element, not comfortable with the interpretation and the explanation that is, in my view, an essential part of what statistics is all about. Now, it goes deeper than that because it's not just about what happens in schools or universities. It's more than just exams and qualifications. Statistical understanding's for everyone. Everybody needs statistical understanding to make informed decisions. Big claim, it's a democratic imperative to enable citizens to play a full part in society. I think we've seen that just recently in terms of COVID, where actually I think the media have made a pretty good effort to communicate the underlying statistics well to people who perhaps are not that used to interpreting statistics. I'm not saying the media have always got it right, but I think they've tried harder with COVID than with most other things that actually have got a lot of statistics in them. If we think back a little while ago to the Brexit referendum, I think a better understanding of the statistics, better understanding of the underlying data might have been useful in informing the Brexit debate. I won't go so far as to say that the outcome would have been different, but it might have been a better informed outcome than it was in fact. But of course, in everyday life, statistical information is often muddled, incoherent. It's expressed poorly in language. And as a consequence of that, if you express the idea poorly, unclearly, incoherently, then statistical reasoning just will not be good. It'll either be missing altogether or it'll be completely misconceived. Now, the sorts of things that we need to talk about in broad outline, we need to talk about much more than just the numbers. It's about the story, the background, the question we're interested in, what we're investigating, the conclusions, how to communicate them. In fine detail, there's an awful lot that we need to talk about. I'm not going to go through that list there, but you'll recognize all of those and more as items that need discussion when exploring what statistics is all about. Now, that obviously is vastly more than I can hope to cover in a 1-hour talk. And what I'm going to do then is to move on straight away to just one very simple item that we need to talk about, the average. You perhaps know the quote, statistician is someone who with one hand in the fire and the other in the freezer says, on average, I feel fine. It's not a very good joke, but it does actually illustrate an important point. And that point is that averages need some indication of variation if they're to avoid being at best misleading and at worst dangerous. And the average, basic idea as it is bedeviled by poor use of language. Now, we're all familiar with the fact that the average can mean a number of different things. We've got the arithmetic mean, we've got the median, we've got the mode. There are other sorts of averages as well, but those are the three most common ones. And then, of course, the average can be typical or ordinary. But there really is an important point here, a point very often overlooked. The very concept of an average implies variation. I've done this with groups of teachers and groups of trainee teachers, student teachers, and said to them, first thing I'd say in a lecture, what's the most important concept in the whole of statistics? And you get an awful lot of blank looks. And I say, well, what's the thing that you learn first? What's the thing that you make most often make reference to? And somebody rather uncertainly will say, well, the average. Yes, the average is just about the most common thing in the whole of statistics. But averages wouldn't exist unless there was variation. You don't talk about the average number of legs on a dog because there isn't enough variation to make the concept worthwhile. And yet that is so overlooked. So if the average is the most common thing in statistics, then that is because the most important thing in statistics is actually variation. Well, let's have a look then at some ways in which the average can be mispresented. This comes from something the Nationwide Building Society published in 2017. The average family consists of 2 children. Well, of course, it doesn't say what sort of average it is. That could be the mode, it could be the mean rounded, it could be the median. It's impossible to know. And you might say, well, does it really matter? That's a slippery slope. It matters because statistics matters, because accurate communication of ideas expressed in statistics matters. This particular item isn't terribly important, but statistics is, and this is just one small symptom of a problem in the way in which statistics is communicated. And most importantly of all, from my point of view, of course, it tells us nothing at all about the variation. The average family has 2 children in it, but what about all the other families that don't? We're not told anything there. Another example, a pair of examples from the same document, the amount spent on a family car is, not is on average, note, but is £8,911. Really? The Ford Focus is the car of choice. Is that the modal choice? Possibly, but again, it's not explained. And we have information about British families enjoying 2 holidays a year. The one in the middle is interesting. 27 is the average age to start a family. Is that for all people who do start families or for all people? Is it for men and women combined or men and women separately? Well, no, it's different for men and for women. So that just raises more questions than it answers. And the average family has 1 pet, with dog being the most popular. Who knows? Very difficult to know what that means. Let's look at something that is a little easier to interpret and yet still has this sense about it that the average might be a little unclear. This again will be familiar to you, if not necessarily to students or people you communicate with. The income distribution, these figures come from 2018, but they're broadly similar year on year. The graph just slides a little bit to the right. And what we have is a mean, which is given on the graph, a median also given on the graph, and the mode, well, we can sort of round the histogram off there, and we can come up with a mode at around about £21,000. So what is average income? Well, if you read the small print in the better newspapers, you will see that the average, as published by the ONS, is the median. But it's very easy to assume that because the word average is used, it's actually the mean. And there's an awful lot of people who would say, you're joking. You know, the average is 28. Well, most people I know are only earning around 20, 21, 22,000, which is, of course, the concept of the mode. And I do wonder, when I look at this sort of thing, I wonder, why is it that we can't just give people the distribution? Why do we feel the need to reduce something with a lot of variation in it, reduce that to a single number? Shouldn't we be saying that the variation is what's really interesting here, and be presenting people with a distribution. And shouldn't we expect that the level of education in this country is such that citizens can cope with a distribution like that and don't need the single number? I'm not, of course, saying that we might not want to give the single number as well, but it's the distribution that shows the variation that tells the whole story. The single figure can't possibly do that, and particularly when the single figure could be one of any of those three. So the average, how it's used, but even when we know which average is being used, how it's used can be a problem. Unclear, inappropriate, misleading, unintelligible. And to make that point, I want you to consider a particular example. I want you to consider camels. Now, think about the implications and assumptions in these sentences. It's not the number, 1.06, trust me, I've done the sums. It's not the number I'm talking about. Think about the language. The average camel has 1.06 humps. Think about the language. Camels have on average 1.06 humps. The average number of humps is 1.06. And then the fourth statement there, most camels have one hump, 6% have two humps. Think about the language and think what the implications are of the different ways of expressing this piece of numerical information. Well, the first of them, the average camel has 1.06 humps. The focus of the sentence, I'm speaking now linguistically, the focus of the sentence is the average camel. The sentence assumes, implies, suggests that the average camel exists, that it is a thing, that it's a useful concept. But of course, the average camel doesn't exist. It's a mythical beast. Camels have on average 1.06 humps. The focus of the sentence is camels. That's perhaps rather better than the average camel. At least camels are not mythical beasts. But it assumes that it makes sense to treat camels as a set of comparable objects. What we've got here is two groups lumped together that should actually be kept separate. The third sentence, the average number of humps per camel is 1.06. The focus is now humps. It assumes that it makes sense to think of humps being distributed among camels. Those of you who are familiar with the Just So stories might imagine the jinn giving out the humps, finding he has some left over when they've got one each, and so he gives the rest out to some of the camels. That's how they got their second hump. So the focus of the sentence is really what I'm looking at in these three examples we've looked at. And I think once you look at the focus of the sentence, you realize in each case, it isn't really addressing what it is that you want to talk about. The fourth sentence, I think, does the job properly. It first of all explains that there are two sorts of camel. There are those with one hump, those with two. Just 6% of camels are in that second category. And of course, the really important element from my point of view here is that what that sentence is doing is focusing on the variation without even mentioning the average. And my point there, knowing which word to avoid can be just as important as knowing which word to use. So some lessons from camels. Avoid mythical beasts. Think carefully before aggregating groups. Get the focus right. What is it that you want to be talking about? And most important of all, think about the variation. Always important, sometimes more important than the average. Big caution, beware of camel averages. So why does this sort of thing matter? Well, go back to the nationwide thing again. I'm not going to look at all these in detail, but the idea that the average family day, well, the idea that it's even meaningful is a very strange one. But the idea that it can then be reduced to these measures taken down to the last minute for cooking dinner, having your first alcoholic drink and so on, is clearly a nonsense. The average home, similarly, is a nonsense. In fact, I think the only reliable figure in that is probably the mortgage, where presumably the nationwide added up the total number of the total value of all the mortgages divided by how many they got and came up with this figure answer, which will have been accurate for a few minutes or an hour or two, and is now, of course, completely inaccurate. More importantly, let's have a look at this one. The average male has one criminal conviction by the age of 52. Okay, well, at the level of dividing the number of convictions by the number of males, that's actually a correct statement. But 67% of males have no convictions. The rest of them have an average of 3 convictions. Of those 33%, there are many who commit just one crime and repent of their ways, and there are those, the lifelong criminals, who commit far more than 3 crimes. This is a very skewed distribution. And I think there's almost a sort of moral imperative here, which is that the 67% of males with no convictions just shouldn't be lumped in with those who do have convictions. And indeed, those who have a small number of convictions and then repent their ways shouldn't be lumped in with the lifelong criminals. In other words, what I'm saying there is that there should not be a process whereby you do any averaging at all. Here, I think that to do that is actually sort of morally improper. And the fact that you can calculate an average is no excuse. It simply shouldn't be done. Why this matters, number 3. The NHS website, Healthy Weight, tells us that the average man needs 2,500 kilocalories a day. The average woman, the figure is 2,000 kilocalories. And then it tells us these values vary with age, size, levels of physical activity, amongst other factors. Well, now, that is on the one hand good because it mentions variation. On the other hand, it's bad because the variation isn't quantified in any way. I looked on the NHS website for quite a long time and struggled, and in the end gave up in my attempt to find any measure whatsoever of what the variation is. So if I, as a man, am consuming 2,600 calories a day, am I going to put on weight? Should I be curbing that excess appetite of mine? Or is 1,000 kilocalories neither here nor there? There's just no way of knowing. There is no measure given. And my point, I've made it before, I'll make it again, that averages without no mention of variation are, well, at best misleading and at worst dangerous. And that particular information from the NHS website is pretty much unusable because it doesn't have with it any sense of variation. Not only does it not quantify the variation, but if you have, for example, the fact that the target levels depend on age, do they increase with age, decrease with age, increase for a bit and then decrease for a bit? It really is worse than useless to be given that sort of information. Number 4, why this matters. Ofqual, I'll have a little bit to say about Ofqual. The corresponding organisation in Scotland is the SQA, and I do know that the two bodies work quite closely with one another, and the statistic that I'm giving here also applies, I believe, in Scotland. So this is an Ofqual meeting where it was pointed out that Ofqual's own research showed about 25% of GCSE grades were wrong, half of them being 1 grade too low and half being 1 grade too high. Now I should explain what's meant by the grade being wrong. The criterion that Ofqual uses is that if the scripts were remarked by the senior examiner, remarked to senior examiner's standards, then 25% of the grades would change. And I do mean 25% of the grades. I don't mean 25% of the marks. Okay, so 25% of the grades are wrong, half 1 grade too low, half too high. Somebody at the meeting, a senior Ofqual person, said, so a typical 8-subject GCSE candidate will get 2 grades wrong, 1 up and 1 down, so cancelling out. That doesn't seem too bad to me. I'll just pause there for impact.
Sorry, Neil, I've muted the wrong person, so you'll need to unmute yourself.
Right, I'm unmuted. Okay, so we had this statement: a typical 8-subject GCSE candidate will get 2 grades wrong, 1 up, 1 down, so cancelling out, that doesn't seem too bad to me. And you've had a little bit of time to think about that. You know, what do you think of that as an analysis? Well, I was rather surprised, actually, that the, oh dear, my screen seized up, excuse me. Not sure what's wrong there. There we go. Nobody in the meeting challenged that. I wasn't at the meeting, but somebody reported it to me. And when it was reported to me, to be honest, I was really quite shocked. I said, was that really what was said? And when you do the sums, it's easy enough. It's just a binomial distribution, assuming that the outcomes are independent for these different subjects marked by different examiners. It turns out that just 16% of the students will get this so-called typical result, and 71% of students will get non-cancelling errors. Now, that's quite remarkable, I think, once you do the sums. It may be that that's what happens on average, but it's not what is typical. And it really does make a very important point, the point that what is typical isn't the same thing as what is average. Let's be clear, on average, an 8-subject candidate will get 1 grade too high and on average 1 grade too low, but that isn't what will happen to most people. 71% of students get non-cancelling errors. Well, I can't talk about off-qual and by implication SQA without talking about the grades fiasco. You'll have seen some of the language that students in particular were using. These are all taken from placards that I saw in the media. And perhaps students, not stats, is the one that stands out there. You know, people, not statistics. And all sorts of comments on the algorithm. I say they were all from the media on student placards. The last one wasn't. The last one was from Boris Johnson. It's all the fault of a mutant algorithm. And it also produced some very polarized argument. And the interesting thing here is that pretty much every statement has a direct counterpart. And you're left wondering which of them is the accurate statement. So did the algorithm downgrade 40% of entries, or were 40% of teacher estimated grades unrealistically high? Again, were children from downgraded disproportionately from deprived backgrounds, or was it that those from deprived backgrounds had their estimated grades inflated disproportionately? And this one I think is particularly interesting. Thousands of children with protected characteristics were downgraded versus the unintentional and unavoidable biases in the algorithm affected less than 0.2% of entries. Well, actually, pretty much all of those statements are true. And in each case, the blue one and the red one are just 2 sides of the same coin. They are 2 ways of looking at the same piece of information. So the cautions: the average can be untypical. A small proportion, that 0.2%, can be a large number, many thousands. And what's fair to a cohort can be unfair to individuals. And that's very much what appears to have happened with the off-qual and SQA algorithms. And back to why this matters. Number 5, The Guardian has what is actually very typical of what journalists write. And here's a statement about life expectancy, and you'll see that the Faculty of Actuaries expects men to die at a certain age and says women are likely to die at some other age. Now, as statisticians, we're going to say, so one's an expectation and another one's a likelihood. That doesn't seem reasonable to me. It doesn't seem at all like the sort of thing that the Institute and Faculty of Actuaries would have been doing. And of course, it's nothing of the sort. It's the horror of repeating the same word that journalists really do try to avoid doing. And what they've done in this case here is they have simply changed the wording. It will be the same statistic being given by the actuaries, but the journalist has changed the wording so that it looks like it's a fresh sentence, a different sentence. And I've put this actually to journalism students, and I've said, well, if you keep changing the wording from sentence to sentence, then people are not going to understand what it is you're writing, to which the response is, yes, but it'll be more interesting that way. And there's a nice paradox. It's more interesting not to be understood. Of course, the right way of doing it would be to present the graph. And here is a graph. It's not the same graph as the data came from, but it is a typical graph showing the distribution of predicted ages of deaths for males aged 65. I don't think it's unreasonable to expect that readers of The Guardian should be able to understand a graph like that, perhaps with the gloss underneath about the mean, median, and mode. I don't think that's unreasonable at all. This one always tickles me, and I've been using this one for years. Every star twinkling in the night sky plays host to an average of 1.6 planets. So pick your favorite star, Alpha Centauri. That's a star twinkling in the night sky. So it plays host to an average of 1.6 planets. The sentence just doesn't make sense. And from the Daily Telegraph, the Australian edition, lovely one this, the average Australian woman has grown since the 1960s, has grown less than 2 centimeters, but put on 7.3 kilos. And then we have the figures for men. And of course, the average Australian woman and the average Australian man are both mythical beasts. But what a wonderful confusion there is there between longitudinal and cross-sectional data. Caution, beware of journalese. And my point, to summarize, is that even when discussing something as simple as the average, we really should be looking to use clear, precise, unambiguous language. Otherwise, we've only got ourselves to blame when we're accused of lies, damn lies, and statistics, proving anything with statistics. Or one of my favorite, statistics is the art of never having to say you're wrong. We as statisticians, as statistical communicators, I think can do, must do, should do better than that. All right, so let's look now at something a little bit more complicated. Let's look at significance. And I've got a couple of lovely quotes here. First of all, the term statistically significant has lost all meaning and turned into a rule. Well, yes, it has, but a rule to enable people to avoid statistical thinking. I love that one. It's like a sort of rubber stamp, you know, statistically significant, job done, next problem for analysis. Far from being the conclusion, of course, determining that something or other is statistically significant ought to be the beginning of the next phase of the investigation. It is not a conclusion. But pronouncing an observation as statistically significant gives, and again I love this, an illusion of certainty in an uncertain world, and people crave certainty. If only they knew that statistical significance doesn't give certainty at all. It is an illusion. And both of those quotes come from Helen McGillivray, the editor of Teaching Statistics. Well, the technical meaning, which goes back to the 19th century, was given prominence by Fisher in the 1920s. But it has always been at odds, I think, with everyday meanings such as worthy of attention, practical importance. And we're all familiar with this, of course. An observed difference can be statistically significant but completely unimportant, or the opposite. And Cohen's concept of effect size in one way is intended to sort of clarify that distinction, but in other ways it's actually just become another way of talking about the word significant. That's a significant result, you know, the effect size is whatever it is. So we've really got a linguistic problem associated with the language of significance. And to illustrate that, I'm actually going to go back to an off-call document again. And this was a document, or rather ironically, really, it was a document on the statistics of grading. And just look at the words significantly and significant in these quotes. So the probability of receiving the definitive grade is significantly influenced. The probability is not significantly different between the original and the revised methods. these statistics are not significantly different. This seems to be at least as significant as the impact of that. You look at those quotes there, and I would defy you to be able to guess, to reason, determine, infer whether the words are being used in their technical sense or in their everyday sense. And you might say, well, you know, surely those are going to be just the everyday usages of the words. But this was in a document on the statistics of grading that did actually contain some hypothesis testing. So you're actually left, I would say, with not the slightest clue what those words actually mean. And if words cannot be understood, we really ought to be doing better than using them. A second why this matters, this is a true story. Candidate for a job, a family friend actually, was asked what it means to say a result is significant at the 5% level. This was in an interview. He said, it means there's a 5% chance, and then apparently he corrected himself and said, no, I mean the 95% chance that the effect being tested for is real. And he told me this, and he said, did I answer the question correctly? A bit difficult to know what to say. What I in fact said was it might very well be the answer they were expecting. It might even be the answer that some of them believe to be true, but of course it is completely and utterly wrong. Well, the interview was for an organization evaluating clinical trials, and this chap was hoping to become an analyst in that organization. He got the job. Now, I find that really ironic. Here is somebody who has what we might term the standard misinterpretation of what significance means, and yet gets a job doing the interpretation of hypothesis tests. Really quite worrying. And I actually then, talking to this family friend, I actually went through a discussion with him, which I've used in the classroom on a number of occasions over the years. So you have a job in the Royal Mint testing coins as they come off the production lines to see if they're fair or biased. And the way you do this is you test each coin by testing it 100 times and counting the number of heads. If you get a value in the range 40 to 60, you put the coin on the accept pile. But if the number of heads is less than or equal to 40 or greater than or equal to 60, you put it on the reject pile. And I would tell the class that the probability of getting less than or equal to 40, greater than or equal to 60 with a fair coin is, roughly speaking, 5%. So the question to the class, what proportion of the coins you test will be in the reject pile? It does take some nudging. They don't get there quickly, but they can be nudged to say, well, it's going to be approximately 5%. Yes, about 5% of the coins will be on the reject pile. Now the hard question, how many of these coins will actually be biased? Yeah, that is the response. Silence. The question's too hard for them. All right, how many coins coming off the production line at the Royal Mint do you think are biased? Takes a bit of nudging, but again, they'll come up with, well, yeah, not many, perhaps none at all. At which point they're totally perplexed. Why have we got this pile of coins on the reject pile when we don't actually think that the Royal Mint produces biased coins? It's going to be a very good production process that produces unbiased coins almost all the time. So how many coins on the reject pile do you think are biased? Bit of nudging again, because they're hesitant, none. Now just think about this from the point of view of the students. They've been taught at this stage what a hypothesis test is, and they know that the coin is to be rejected at 5% level as being biased. And yet when they go through this exercise, what they're saying is, I've got a pile of these coins that have failed the hypothesis test, but I don't actually believe that any of them are biased. What on earth is going on? So let's make it worse for them. We say now, let's suppose you're working for a pharmaceutical company and you're looking at drugs that achieve 5% significance, properly conducted clinical trials. How many of those drugs are actually of medical benefit? And that's a really, really hard question for the students. But with a bit of steering, the conclusion they're going to come to, there's no way of telling. It could be none of them, it could be all of them. So they're left wondering, what does a 5% level of significance actually mean? We're totally confused. Well, their confusion's something that needs sorting out, but in the meantime, they're actually in a better place than they were at the start of this discussion, because they no longer think that failing a 5% test means you've got a biased coin. They realize there's got to be something else going on. They realize that other factors need to be taken into account. So what we're actually doing is we're saying, as statisticians, that what happens in a significance test tells us pretty much nothing at all about whether the effect we're looking for is actually present or not. Saying the result is significant at a particular level, the 5% level, as we saw in the story of the interview candidate, just makes the matter worse, because now there's a temptation to quantify the likelihood of the effect being absent or present. And once you try and do that, of course, you get it wrong. And my point, my linguistic point, is that the word significant doesn't apply to the effect. The word actually applies to the data, and it's confusion about the language that's leading to confusion about the methodology. But most users, of course, don't see it that way. They don't see the problem. And I think it is for us as teachers, us as communicators of statistics, to actually do the job of communicating what's going on rather better. So my fourth bullet there, a significant result is one that is somewhat out of the ordinary if there's no effect present. That's not how it's widely misunderstood, but that's what we've got to convey. And that is just another name for an outlier. If the null hypothesis is true, then what we've just observed is an outlier. Now, students know about outliers. They meet those at, well, in England at GCSE, whatever the corresponding level is in Scotland. And if they know about it, build on the familiar. It's a better way of developing understanding. They know that outliers sometimes occur by chance when there's no effect, and they know that sometimes outliers indicate that there is an effect influencing outcomes. And outliers need then to be scrutinized further. And that's pretty much what Fisher had in mind when he used the word significant. Not that this was a conclusion, a rubber stamp, but an invitation to do a little bit more investigation. And using this language, the language of outliers, makes it clear that we're talking not about the effect, but about the data. You do see statements like, the effect is significant at the 5% level. No, that's wrong. It's the data that are significant at the 5% level. Do some investigation before you rush to conclusions about the effect. So I'm saying that a change in language carries with it an improved understanding of the rationale of the method. So I'd like to see the vocabulary as significance. Well, I'd like to see it banished forever. I'd like to see results described as 5% outliers or 1% outliers or whatever. Get rid of the troublesome terminology and replace it with terminology less susceptible to misinterpretation. I dare say I'll never get away with that. It's too revolutionary. But we could carry the two vocabularies in parallel. Talk about outliers, excuse me. I'm drying up. Talk about outliers in order to explain significance. At the very least, I think that would head off the wrong answer to the interview question in My True Story. Had the candidate understood significant results as outliers, then I think he would have made a better fist of answering the question. Now, of course, it's also the logic of significance that goes wrong. And the common misinterpretation is that a significant result is saying that the null hypothesis is likely to be false, the alternative hypothesis is likely to be true. That's a logical error. It gets conditional probability the wrong way round. These two are commonly confused. The conditionality is reversed, But of course, the logic is exactly the same as this logic here. And I don't think anybody would expect that those two conditional statements about cats and their legs were equivalent or easily confuse the one for the other. And yet it's very widespread to misinterpret the relationship between observations and the truth of the null hypothesis. Again, as communicators and teachers, it's perhaps the case that we just need to do better to make sure that these rather subtle points perhaps are better understood. There's a parallel with criminal trials. These two are commonly confused. The probability of the DNA matching, given that the defendant is innocent, and the probability the defendant is innocent given matching DNA. I actually attended a couple of years ago a conference for lawyers at which this problem was given extensive coverage from the front by some statisticians. And over lunch, I did actually hear some lawyers speaking to one another along the lines of, well, I still don't really understand what the difference is. It seems to me those two statements are saying the same thing. So we really do have a challenge on our hands to make sure that this sort of concept is well understood. And the really important element, of course, is that you can't just identify guilty parties using statistics. You need a lot more than that. In particular, you need an awful lot of background information. And I'll say in a moment that that's exactly what we need in statistics too. Just briefly, another true story. Some of you will be familiar, I think, with the case of Sally Clark. She had two children, both of whom died from cot death, and she was convicted of murder. And the prosecution case, which was actually riddled with errors, but it did rest on confusing these two. The probability that there are two cot deaths given that she is innocent being very small, which it is, and the probability that she is innocent given that she has had these two cot deaths being very small, which is of course not necessarily true and certainly is not deducible from the previous statement. That and a number of other statistical errors were made in the trial, and the RSS, to its great credit, did make quite a lot of fuss about getting the verdict overturned on appeal. But by then, Sally Clark had spent 3 years in prison. She'd developed psychiatric problems and died from alcoholic poisoning. So getting this sort of thing right really, really matters. So why do we reject null hypotheses on the basis of significant results? I think this can be explained in terms of different forms of inference. We're familiar with deduction, logical reasoning, following axioms through to their logical conclusions. That's what mathematicians do. Induction, arguing from cause to effect, familiar to scientists. If I do this, then the following will happen, going from cause to effect. And statistical inference isn't doing either of these things. It's actually more like going from effect to cause. I observe the effect. Can I infer anything about the cause? Well, you can't do it deductively. It's not a logical thing that you're doing. And you can't do it inductively because that's working backwards. It's got to be a different form of reasoning. And Charles Sanders Peirce in the 19th century proposed a third mode of inference. He called it abduction, which is perhaps a slightly unfortunate term because of its other meanings, but he said that argument from effect to cause, or argument to best explanation, is really what we need to be using in this case. And we can see hypothesis testing in that way. When all the background information is factored in, the observed results are best explained by supposing that the null hypothesis is false. But the key phrase, when all background information is factored in, the numbers alone, the data alone, the statistics alone cannot settle the matter. So let's try and interpret a couple of our examples in terms of abduction. The coins example. If we factor in the background information that the Royal Mint doesn't make biased coins, that tells us that a significant result is unlikely to mean that a coin is biased. So argument to best explanation, abduction, suggests that chance is responsible for the observations. And that, I think, is an important perspective to have. It's important to be able to have a principle on the basis of which you come to a conclusion like that. Another example, the Higgs boson. When the Higgs boson was claimed, its existence was claimed, it was on the basis of a significance level of 0.123456003. A CERN scientist was quoted, and I was delighted that the quote is correct, because so often talking about these things is incorrect. This is not the probability of the Higgs boson existing or not. It is the probability that if it doesn't exist, the data would be at least as extreme as what was observed. An accurate statement of what a p-value is. And of course, if you use abduction, you say the existence of the Higgs boson is the best explanation we have of such extreme data. So I think abduction as a principal argument to best explanation is an effective and important way of interpreting statistical results. Some online explanations, which I've included really just to illustrate how bad they can be. In many cases, I struggle to understand what it is that the author's trying to say. There's a 5% probability the means are not due to chance. That defeats my understanding. The significance test assigns a probability level to describe the likelihood that the null hypothesis is true. And I think I can see what the author of that one's getting at, and it's wrong. If the p-value is less than 99% of the means, chance of the means being significantly different. Nope. What about this one? Our data are good enough to support a conclusion with 95% confidence. I think that one was paired with an explanation of 95% confidence, as saying that the data would fail a 95% significance test. So it also had circular reasoning built into it. There is indeed a long way to go. Now, I'm sure that many, all of you will be familiar with the ASA statement on p-values, and I'm not going to spend any time particularly going through those, other than to say that, broadly speaking, I agree with what they're saying. The p-value on its own really doesn't do the job. It's only an indicator that you want to put alongside an awful lot of other indicators before you come to any sort of a conclusion. The ASA don't suggest that p-value should never be used, but of course some, well, at least one, I think other journals have now done that, but does say that statisticians often supplement p-values with other approaches and include methods that emphasize estimation, such as confidence intervals, and I would also say things like bootstrapping and so on. What they don't say there, but I think they certainly intend, is that other background data, other information, the sort of thing that you'd want to have in order to be able to use abduction would be brought in. All right, let me wrap things up. You will have noticed the presentation hasn't been about the numbers, the calculation, or the formulae or the graphs. It's been about the language, how to use language to understand terminology, explain methods, and interpret results. There's an important point, I think, which is that statistics uses mathematics, like physics or economics or engineering, but isn't mathematics. It's a much broader skill set than that, and that has to be seen as a positive, not a negative light. That point I make because for some teachers, it's certainly the case that the broader skill set of analyzing in language the uncertainties of the real world leaves them less comfortable than they are when they're dealing with pure mathematics. And I also would say that we've got to recognize that statistics is important across a wide range of academic subjects, and particularly in everyday life. It's not just an academic matter. It's subtle in its use of language, it's widely misunderstood, and if we're to do better, then we have to use careful and accurate language in our teaching, learning, and in the assessing and communication of the subject. So the teachers, and this does come from the origins of the talk, accept that statistics is distinct from mathematics and has its own skill set, recognize that it's discursive, be comfortable using and analyzing language, be creative and flexible in the use of language, and be rigorous in the use of language in order to achieve clarity and accuracy. And if those are the sorts of things that teachers need to do, well, I'm saying that so too do all those who communicate statistics. And it's not just me saying it. The August 2020 Significance magazine landed on my doormat yesterday, and I was pleased to see this from, actually from Alan Rees, quoting David Hand. All too often analyses are undertaken without sufficient thought being given to the genesis and the provenance of the data. And then Alan Rees's comment on that, the problem lies in viewing statistics as a branch of mathematics, and he asks that statistical education should recognize that there are philosophical and epistemological issues which are complementary to the application of statistical methods. And from me, hear, hear. So statistics is not just mathematics. The language of significance is damaged beyond repair. The logic is widely misunderstood. Can we please abolish significance testing altogether? And can we recognize that the purpose of statistics is insight, not numbers, and insight is expressed in language? Thank you for listening.
Thanks very much, Neil. That was really interesting. So I have put the link and code for the Menti back into the chat. So if you do have any questions, please go to that and feel free to fill that out. So kind of, we have had a few questions already. So I'll just ask one of those while we wait on some to come in. But you were making the point about significance testing and the language that surrounds significance. So someone has asked, how then would you explain a significant result to the public? So someone who doesn't have a statistical background.
Well, I think I would want to try to build on my concept of it being an outlier. If the null hypothesis, you'd have to find another word for the null hypothesis if you're talking to a non-specialist. But if the area we're investigating is such that, then put the null hypothesis into words, then we wouldn't expect a result like what we've just seen. It's really rather an unusual result. That doesn't mean to say our assumption is false, but it does mean to say we've got to do a bit of investigating. We need to look a bit more at the background. Maybe we need to find out, get some more data. We certainly need to regard this as an interesting phenomenon, but it isn't in any way conclusive.
Okay. And then we've had another comment asking, would the use of Bayesian statistics help to solve some of the problems that you've mentioned? So, for example, transposed conditional probabilities.
Yeah, I think it would, and I think it does. But in what I've been saying, I've deliberately avoided using any of the mechanisms of Bayesian or the language of Bayesian statistics, because what I was trying to do was to get the thing away from the technical language that has gone so badly astray into a more intelligible form of language. And the problem about using Bayesian language explicitly is that it actually then becomes less intelligible to the majority. But what I said about abduction, the argument to best explanation, is Bayesianism without the technicalities. It's saying that we can't just take into account the result of the hypothesis test. We have to factor in, you don't call it this, but you have to factor in the prior knowledge. So yes, it is Bayesianism without the language being used. The other point that I do feel about Bayesian inference is that it can be difficult and indeed counterproductive some of the time to suppose that you can attach anything like a precise prior to the the unknowns that surround what you're investigating. And I do feel a little bit uncomfortable about attempting to do that. And I'm not even then comforted by the notion that once you get enough data, it'll converge to the right thing anyway. It just looks to me as though it's a little bit like the sort of thing that in those quotes from Helen McGillivray, she was criticizing. It's a variation on this sense of, I want certainty, even if it's the certainty that's expressed by a distribution rather than by a simple binary accept or reject. And I feel much more comfortable with statistical conclusions that are not certain, but actually continue to talk about the uncertainty because that's a feature of the real world.
Okay, and then one final question, which I'm particularly interested in as a person who teaches regression modelling. How would you propose that we discuss the results of a regression model, for example? So this person is not 100% convinced that use of the word outlier would work.
I'd need that explaining a little bit, but I would have thought that in a sense, when you're doing a regression model, particularly when you look at the graph of a regression model, you've got a very clear sense of outliers. I must be misunderstanding the question.
So I think it's the way that I've interpreted that is with respect to sort of testing the slope of a model fit.
Oh, I see. Yeah, well, I don't think I'd want to test the slope anyway. I think what I'd want to do is I'd put a confidence interval around it. Now I know there are those who say that they're just two ways of doing the same thing. I'm not convinced that is true because I think that the confidence interval approach actually incorporates it's sort of philosophically different, it's epistemologically different, to come to the point that Alan Wentz was making, because the very way in which you express yourself actually encompasses the uncertainty. But if we insist that we want to do this in terms of outliers, then you say something like, well, I've got a null hypothesis that the true value of the slope is whatever. The value of the slope that comes from the data is something else. If that is sufficiently far away from what was originally hypothesized, then I may simply have got an outlier. Wouldn't that be exactly the same as in the simple case of a proportion or a mean?
Okay. That's great. So there's a couple of people asking if a recording is going to be made available. So that will be made available on our YouTube channel. We will send that around our mailing list, and I will pass that on to the Teaching Statistics Special Interest Group so that they can send it around their members. So you will have access to a recording. Someone else has asked, would you recommend any reputable sources of where you might be able to find more information about correct use of statistical terminology? So maybe if you could send me some of those, if you have them, and I can pass them on to everyone who's here as well.
Could I put in a plug for David Spiegelhalter's book, The Art
of course you can.
Which actually was one of the slides I took out. I thought, I'm going to run out of time, I'll take that one out. But David Spiegelhalter just does an absolutely brilliant job of explaining the sorts of things that, well, let's put it this way, if I had been able to write a book as good as that on more or less my theme, I would have been very, very proud indeed. He's done a brilliant job.
Okay, that's great. So thank you again, Neil, for giving us the very interesting talk, and thank you to everyone for coming.